Hey everyone, I hope you had a safe and pleasant last week, and I hope the quarantining and shelter in place is actually helping you work and study efficiently as it is to me. Um, a few things first. Heads up, you have the homework due in less than 10 days, that is on the 13th of April. Um, Also, I wanted to thank all the students for the kind words that they have poured in on the email, and I hope I responded to almost all the queries addressed to me. Also, while emailing me, please have the subject line as ECS 20 in the big brackets so that because I um, uh, filter my emails for the class queries using that. The dog is Aussie. He's my lab neighbor, so just in case anybody else had the questions. Okay, let's dive deep. We're gonna have we'll go over basic proof techniques and induction techniques while starting with some brief about proposition this time. Let's look at what propositions are. So, a proposition is a statement or assertion that must be true or false. A predicate is a template for a proposition. We'll go on what a predicate is. A predicate has a truth value and that is a true or false. Example, so phi is a prime. I mean, it can be true or it can be false. Every cow has four legs. That is true. But when I say sit down, it's more of an order or a sentence than a statement, and hence it does not have a true or false value. X plus 2 is equal to 3 is just a sentence because I haven't defined what values can X take. If I say that any other true value, like the sun rises in the east, now it has a true or false statement or a value. So if a statement has a true or false value, it is called a proposition. A propositional variable, that is, it is defined by lowercase letters, is a proposition. These variables model true or false statements. The negation of a proposition P is written as negation of P. This is the symbol that you use. So if I say the sun rises in the east, the negation is the sun does not rise in the east. The conjunction of two propositions is written as P and Q. This is the symbol for and it is a proposition. So P and Q is the conjunction. The disjunction is or, and it's written by the symbol. Sorry. The conditional statement that P implies Q. This is P implies Q. So I'll say, if it rains, then I'll carry an umbrella. So if it rains, I'll carry an umbrella. So it rains is P, and Q is I will carry an umbrella. Consider the following propositions. Statement P says that Jai is a CS major. Statement Q says Jai is a PhD student. Can we try to use the symbolic connectives we used to represent Jai is a CS major but not a PhD student? So Jai is a CS major, that's the first sentence, but not a PhD student, right? So how do we write that? So this is P and not Q. So Jai is a CS major, but can also be written as and not Q. So Jai is a PhD student is Q. So Jai is not a PhD student is not Q. So we write it as P and not Q, which can be symbolically shown as P and not Q. So a proposition is P implies Q. So the statement P implies Q can be written as if P then Q, Q if P, and P only if Q. And you can write sentences in these formats if you want for P implies Q. A contrapositive is a statement that is written as not Q implies not P. Now, the contrapositive statement is equivalent to the propositional statements. So if I write P implies Q and I write not Q implies not P, both of them are logically equivalent, and we'll see through the following lectures that professor takes in the future. A converse statement is if P then Q, that is, if Q then P. Inverse is if not P then not Q. Alright? So we'll do a question. The statement is if Taylor Swift won a Grammy for Album of the Year, then Buzz Aldrin landed on the moon. So let's break this into implication. So we have if, then. So this is our first proposition, that is P, and this is the second proposition, that is Q, right? I wrote P and Q here. All right. Then how do I write not P and not Q? So I just negate the first statement. So Taylor Swift did not win a Grammy for the album of the year, and Buzz Aldrin did not land on the moon. All right, so that's not P, not Q. Let's look at how we'll write the inverse of this statement. That is, if not P, then not Q. Take a minute to try to answer this question. You have P, you have Q, you have not P, you have not Q. Write this inverse statement of P implies Q. And the inverse statement is written as not P implies not Q. So just negate it and just write it in your own words. Let's take a minute for that. Okay, so an inverse can just be written down as if Taylor Swift won a Grammy for Album of the Year, then Buzz Aldrin did not land on the moon. Oh, this is wrong actually. So this is supposed to be if Taylor Swift did not win a Grammy for the Album of the Year, then Buzz Aldrin did not land on the moon. Okay, so next question. Let's write the converse of the statement, and the converse is written as if Q then P. That is, you just write it as if Q then P. So you have Q right here and you have P right here. So if Buzz Aldrin landed on the moon, then Taylor Swift won a Grammy for Album of the Year. Okay? If Q, then P. A contrapositive statement is the one in which you write not Q implies not P. So not Q is Buzz Aldrin did not land on the moon, implies Taylor Swift did not win a Grammy for Album of the Year. So that can be written as if Buzz Aldrin did not land on the moon, then Taylor Swift did not win a Grammy for Album of the Year. Perfect? So let's move on. So that's converse, inverse, and contrapositive of a statement that you're given. You're given P, if P implies Q, you wrote down P, you wrote down Q, you wrote down not P, not Q, and you wrote down the contrapositive, converse, and inverse in terms of the symbolic connectives that you had. Okay. Here's a question for each one of you. Write the converse, inverse, and contrapositive of if today is Sunday, then it is a holiday. If today is a Sunday, then it is a holiday. So write down the symbolic form is P implies Q, and P is today is Sunday, Q is it is a holiday. Write the converse, inverse, and contrapositive statements of the proposition you're given. I'll give a minute for that as well. So you're given the statement if today is Sunday, then it is a holiday, and the symbolic form is P implies Q, and from there you find P, you found Q. Now write the converse statement, the inverse, and the contrapositive. A converse is Q implies P, inverse is not P implies not Q, and a contrapositive is not Q implies not P. Right? So let's dive deep. So the converse statement is if it is a holiday, then today is Sunday. The inverse statement is if today is not Sunday, then it is not a holiday. That is not P implies not Q. Contrapositive is if it is not a holiday, then today is not a Sunday. That's not Q implies not P. Another question, if it rains, then I will stay at home. So you have the P, you have the Q, you have the symbolic form. We did the same question earlier. Give yourself 30 seconds to do this same question again. The sentence is, if it rains, then I will stay at home. And you need to find the converse, inverse, and the contrapositive statements. Okay, so the converse statement, that is, you'll have, if I will stay at home, then it rains. So that is, Q implies not P. The Q was, I will stay at home. So if Q, then it rains. That is, then P. So if Q, then P. The inverse is, if it does not rain, then I will stay at home. That is, not P implies not Q. Contrapositive statement is, if I will not stay at home, then it does not rain. Okay, so that's the three statements from P implies Q. We found the converse, inverse, and contrapositive. Let's look at what proofs are. We're going to look at our proofs. So proof is a formal, general, precise mathematical logic that begins with premises to establish a conclusion. So that is in brief just your existing knowledge. You keep on writing that down and combining different primitives to get to a conclusion that you require. So that's how you prove. Okay. Let's look at, there are different ways to prove, actually, mathematically speaking, but we look at a couple of them, actually four of them today, and there are a lot of other ways you can prove statements. The first one is a direct proof. Now in direct proofs, what you do is, if you have to prove that if n is odd and n square is odd, so if n is odd, then n square is odd. So in this is an implication itself, that if P, then Q. So you start by assuming the statement P and you get to Q. So your existing knowledge is, if n is odd, then n square will be odd, right? So let's get into it. I write that assume n is odd. So n is 2k plus 1. So this is how you write numbers. The whole real number line, I mean the integers, can be written as 2k and 2k plus 1. Building on the last class's example on writing the real number line as the first 100 whole numbers as 7k, 7k plus 1, 7k plus 2 till 7k plus 7. Sorry, 7k plus 6. Because if I'm writing 0, I can write it as 2k, that is 2 times 0. When I write 1, it is 2 times 0 plus 1. I write 3 as 2 times 1 plus 1. I write 4 as 2 times 2, 5 as 2 times 2 plus 1, right? So all odd numbers are 2k plus 1 and all even numbers are 2k for any integer k, alright? So here we established that you can write all odd numbers as 2k plus 1, and here's a heads up. If you ever get a proving statement that requires you to prove, like, if some number is odd, usually the best way to approach is writing it in the form of 2k plus 1. Okay, alright, so I assume that n is 2k plus 1. I write n square as 2k plus 1 the whole square, which will open up as 4k square plus 4k plus 1. I just opened this up like a plus b the whole square. I had a square plus 2 times a b plus b square, right? Now you need to see 4k square plus 4k can be written as 2 times 2k square plus 2k plus 1, where because k is an integer, this value will also be an integer, that is 2k square plus 2k will be an integer. because if k is an integer, then k square will also be an integer, and 2 times k would also be an integer, right? So n square is written as 2 times some integer value plus 1. Now, isn't that the definition of an odd number? That if a number can be written as 2m plus 1, it will be odd, right? Where m is some integer 2k square plus 2k. So hence, we just said that if n square is, hence n square is also odd when n was odd, right? So we just proved that n is odd, then n square is odd as well, right? You can try to do it as if n is even, then n square is also even, by saying that n is 2k, n square is 2k the whole square, and write it in the form of 2 times m, and say that when n is even, then n square is also even. So that's the form of direct proof. You assume the first statement, then you try to prove the conclusion from that. Prove mathematical statements is proof by contraposition, and here you get a statement, you write the contrapositive statement of that, and then you further it. Okay, so let's start. If n square is even, then you want to prove that n is also even, right? The other way around than we just talked about with the direct proof. That is, if n is even, then you prove that n square is even. We prove that we have to prove that if n square is even, then n is even. Okay, all right. So the contrapositive statement of this implication becomes, if n is not even, then n square is not even, right? So that is, if p then q, it becomes if not q then p, then not p, right? So now you just have another statement that you can prove with any other proof method, right? So let's get started with the direct proof to prove if n is not even, n square is not even, right? All right, so we assume that n is not even, that is if p, right? And we get n is 2k plus 1, because we just know that it's very similar to the earlier proof. So the only point here is that if you were given this implication, you wrote the contrapositive statement out and you proved it using a direct proof or any other kind of proof if you want, right? So you assumed n is odd, you write it as n is 2k plus 1 for any integer n, any integer k. Oh, this is the same thing, yeah. And then you write n square as 2k plus 1 the whole square. You open the statement up, that is 2k plus 1 the whole square is 4k square plus 4k plus 1, and which can be written as 2 times 2k square plus 2k plus 1, right? And this is just any other odd integer that you have, right? 2m plus 1, that represents an odd integer. Okay, so this is where you proved that n square is odd when n is odd. So that is, n square is not even when n is odd. That is, n is not even. So that's the proof, that you proved the contrapositive statement. And we know that an implication and its contrapositive statements are both equivalent, and hence if you prove the contrapositive statement, you just prove the implication once again, right? So yeah, n square is, hence by contraposition we prove that if n square is even, then n is also even when n is an integer. So this is called proof by contrapositive statement or contraposition, right? So yeah, that's it. You are given if p then q, you write the contrapositive as if not q then not p, and you assume not q and you go down till you prove not p, and then you'll have the proof by contraposition. The method that we look at is proof by contradiction, where we have a statement that we need to prove. We assume that the statement is actually true, and we actually prove that we assume that the negation of the statement is true and show that it did not. So we prove that that negation of the statement that we assumed to be true is actually false, and we conclude that the statement is true. All right. So you start with the negation of the statement, and you get to prove that the negation of the statement is false, which implies that the statement was actually true. Okay. So we have to prove that root 2 is irrational. So as I said, we assume that root 2 is not irrational. That is, root 2 is rational, and we prove it is wrong. All right. So we know the identity of rational numbers, that if a rational number n, it can be written in the form of p by q, where p and q are co-prime numbers, and q is less than 0. Q is not equal to 0. That is, the denominator is not 0, and p and q are co-prime. Now, what do I mean by p and q are co-prime? So prime numbers are numbers that have only multiples of 1 and the number itself. Co-prime numbers are a pair of numbers that do not share any factors. So if I say 2 and 3, they both are co-prime because they both are co-prime together because the factors of 2 are 1 and 2, factors of 3 are 3 and 1. But if I say 2 and 4, they're not co-prime because they share the factor 2, because 4 can be written as 4 times 1 and 2 times 2, and 2 can be written as 2 times 1. So 2 has factors 1, 2, and 4 has factors 1, 2, and 4, which they share the factor 2, and hence P and Q are not coprime there, right? So P and Q, when I say P and Q are coprime, that just means that they do not have a common multiple, right? So let's go into it. We assume that root 2 is rational and it can be written in the form of P by Q, where Q is not equal to 0. So I write root 2 as P by Q. A square on both sides, I have 2 is equal to P square divided by Q square. I take Q square on the other side, I write 2 times Q square is P square. Now, if I'm writing 2Q square is P square, then P square is actually a multiple of P. Sorry, P square is a multiple of 2, right? And if P square is a multiple of 2, then P is also a multiple of 2, right? 2Q square is P square is a multiple of 2, and if P square is a multiple of 2, then P is also a multiple of 2, okay? So, if P is also a multiple of 2, you can write P as 2 times M for some integer M, right? And now for some, if you write P as 2M, you can write 2Q square as 4M square. From P is equal to 2M, you just put it here, and you have 2Q square is P square and P is 2M, so you have 2Q square is 4M square. I take the 2 out on both sides, and it becomes Q is 2M square. Q square is 2M square, alright? And since Q square, so now, as we saw that P square is a multiple of 2, here Q square becomes a multiple of 2 as well. And which is a contradiction. So if Q square is a multiple of 2, then even Q is a multiple of 2. Sorry, it's right here. Yeah. So Q square is a multiple of 2, and if Q square is a multiple of 2, then Q is also a multiple of 2. Now, if Q is also a multiple of 2 and P is also a multiple of 2, that is a contradiction to the assumption we made that P and Q are coprime. So we assumed that root 2 is rational, and we proved that it is wrong because they both are coprime, right? Because the property of a number to be rational is P and Q are coprime, but here we proved that P and Q are not coprime, and hence that is the contradiction. And by contradiction, we proved that the assumption was wrong and the original statement holds true. That is, root 2 is irrational. Now, a good question to solve for this is to prove that root P as in Philadelphia is irrational for any given prime integer. Uh, Try that, and if you have any questions, let me know. So the question is to prove that root P as in Philadelphia is irrational. The method that we're going to learn is about principle of mathematical induction. So induction in its truest sense is a truth of a statement about one value, that is n0 or 0, n0 right here, that's the base case, and which implies that if we have knowledge that n implies the truth about the next value n plus 1. So we prove that the base case holds true, and then you assume that P of n holds true, that the proposition for the value of n holds true, and we prove that P of n plus 1 holds true. It's more like the domino effect that we have. Like line up any number of dominoes in a row, knock the first one over, and they all fall down. So that's what induction is. It's similar to the ladder principle written in the textbook that says that if we can climb from one step of a ladder to the next higher step, we can reach any rung above the first rung that we know we can reach. So we know that the first rung can be reached, and we also know that if from one rung that we are at, we can go to the higher step, assuming that P of n holds true, right? So we prove that P of n0 is true, the base case, and we assume that P of n holds true to prove that P of n plus 1 is true. Okay, let's do a question, and I think we'll get a better understanding of that. The question is, we have to prove that 3 raised to n minus 1 is always a multiple of n for any integer n. Sorry, any natural number n, right? So the basic step would be that n is 1, right? That's p of 1, and you put the value right there. 3 raised to 1 minus 1 would be 2, which is a multiple of 2. So the base case holds true for that. Now we do look at something called the inductive hypothesis. We hypothesize that p of n is true. That is 3 raised to n minus 1 is a multiple of 2, right? So this was the first step, that p of n 0 is true. Now we assume p of n is true. That says that 3 raised to n minus 1 is a multiple of 2, right? So when I say that 3 raised to n minus 1 is a multiple of 2, when I say any number is a multiple of 2, can I write it as 2 times m for some integer m, right? So 3 raised to n minus 1 is 2m. I can write 3 raised to n as 2m plus 1. Now, this is a given result that we need to keep in our head. Now, we need to prove that p of n plus 1 holds true according to the principle of mathematical induction. That is, 3 raised to n plus 1 minus 1 is a multiple of 2, right? So we need to prove that p of n plus 1 holds true, and the LHS becomes 3 raised to n plus 1 minus 1 is, so I divide 3 raised to n plus 1 as 3 times 3 raised to n. I'm distributing the powers of n plus 1 as 3 raised to 1 and 3 raised to n. Now placing the value of 3 raised to n from right here, we get, so we just put the value of 3 raised to n here. That's 3 times 2m plus 1 minus 1. We solve that, we have 2 times 3m plus 2, now which is actually 2 times some integer that is even. So that says that even p of n plus 1 holds true, because 3 raised to n plus 1 minus 1, that is right here, 3 raised to n plus 1 minus 1 is a multiple of 2. That holds true, assuming that p of n was true, right? So that is the principle of mathematical induction. Let's go over this once again, and I'll look back at the example we had right here. If you first prove that the base case holds true for some n0, then you assume that p of n holds true, and you prove for p of n plus 1. Okay, so let's go to the question, our solution again. Yeah, so that the basic step was for n equal to 1. You just put the value of n to be 1, and you see if the proposition holds true. That is 3 raised to 1 minus 1, that is 2, is a multiple of 2 itself. The inductive hypothesis is p of n is true, that is 3 raised to n minus 1 is a multiple of 2. And when I say a number is multiple of 2, I can write it as 3 raised to n minus 1 is 2 times m for some integer m. So 3 raised to n is 2m plus 1, and then you prove for p of n plus 1, that is 3 raised to n plus 1 minus 1 is a multiple of 2. You divide the powers of 3 raised to n plus 1 as 3 times 3 raised to n, and you place the value of 3 raised to n from p of n. So the assumption was that 3 raised to n minus 1 is a multiple of 2, and we had to prove that 3 raised to n plus 1 minus 1 is a multiple of 2, which we do right here. And that's the proof of induction. Like, so by mathematical induction, we showed that 3 raised to n minus 1 is a multiple of 2. Let's do one more question. Prove that 1 plus 3 plus 5, that is all the odd integers up till 2n minus 1, if you sum all of them, you have, the summation is n square. That is, the summation of the first n odd natural numbers is n square. I've just put the solution right here. Let's just look at it. The basic step is that n is equal to 1. You put the value of n to be 1. You have 2 times 1 minus 1, that is 1 itself. The LHS is 1, and the RHS is 1 square because it's just one natural number. So 1 is 1, that holds true. The inductive hypothesis is for n equal to k, that is p of k. 1 plus 3 plus 5 till 2k minus 1 is equal to k square. So that's the assumption that we're going to hold to. Now since it is true, this is the result we'll keep on looking at. Now we need to prove that p of k plus 1. What does p of k plus 1 state? That 1 plus 3 plus 5 up till the k plus 1th odd number, the summation of that will be k plus 1 the whole square. Now here's the interesting bit. Look at these are the first k odd numbers, and then we add the k plus 1th odd number, right? We already know that the summation of the first k natural numbers, these are the first k natural numbers, is k square, right? So I just replaced these numbers, the first k natural numbers, the summation of the first k odd numbers, as k square. So this is k square plus 2 times k plus 1 minus 1, which we get right here as k square plus 2k plus 2 minus 1, which is k square plus 2k plus 1. When you factorize it, you get k plus 1 the whole square, and that is the RHS. So the summation of the first k plus 1 odd natural numbers is k plus 1 the whole square, which is p of n plus 1. So we assumed right here that p of k held true, and we proved right here that the LHS, that is the summation of the first k plus 1 odd natural numbers, is equal to k plus 1 the whole square, right? So we assumed p of n, and we proved that p of n plus 1 held true, right? One more question. The question is, we're adding the first n powers of 2, so 1 plus 2 plus, so this is 2 raised to 0 plus 2 plus 2 square plus 2 square plus, sorry, this is 2 raised to 3, and so on. And the base case here would be 0. Why? Because the first right here is 2 raised to 0, right? So you put n as 0, you get 1 here, and this side you put 0, you have 2 raised to 1 minus 1, that is 1 as well. I just change it right here. So this is 2 minus 1, that is 1. So the LHS equal to the RHS. The inductive hypothesis would be for n equal to k, that is p of k is true. So you add the first k powers of 2, you get that. So right here, that 1 plus 2 square plus 2 raised to, this is actually 3, till 2 raised to k is 2 raised to k plus 1 minus 1. And the inductive step would be that since p of k holds true, this value is correct, like this is the assumption that we'll make, and we prove that 1 plus 2 square plus 2 cube plus all the first k powers plus k plus 1th power is equal to 2 raised to k plus 1 plus 1 minus 1, right? Right here, look at this. This is what we need to prove. So here, the LHS, the left hand side is right here. We have the result for the summation of the first k powers right here, that is 2 raised to k plus 1 minus 1. That's what we substitute, and we get 2 raised to k plus 1 minus 1 plus 2 raised to k plus 1. Now, we have 2 raised to k plus 1, so we just multiply both of them. We have 2 raised to k plus 2 minus 1. That is the RHS that we need to find. We need to prove. This is right here. So we assumed that p of k holds true, and we proved that for p of k plus 1, right? The base case, n is 0 because it starts from 0. You assume for p of k, you prove p of k plus 1, right? One more question. Prove that 7 raised to n minus 2 raised to n is divisible by 5 for all n belong to natural numbers. So here the first basis step would be for n equal to 1. That's just 7 minus 2, that it would be 5, which is divisible by 5. Inductive step hypothesis is for p of k, that is p of k is true. So you put the value of k in in place of n. You have 7 raised to k minus 2 raised to k would be divisible by 5. So you can write it as 7k minus 2k is 5m for some integer m, right? So we need to prove for p of k plus 1 that 7 raised to k plus 1 minus 2 raised to k plus 1 is divisible by 5. So that is 7 raised to k plus 1 minus 2 raised to k plus 1 is 5n for some value n. The LHS is 7 raised to k plus 1 minus 2 raised to k plus 1, right? So from this result, can we write that 7 raised to k is 5m plus 2 raised to k? That's right here. I broke 7 raised to k plus 1 as 7 times 7 raised to k, and I put in the value of 7 raised to k from here, that is 5m plus 2 raised to k in this, and I open the brackets. I got 5 times 7m plus 7 times 2 raised to k minus 2 times 2 raised to k. Now 7 times 2 raised to k minus 2 times 2 raised to k would be 5 times 2 raised to k right there, right? I took the I factored 5 out of that, so that's 5 times 7m plus 2 raised to k, which makes which results in that 7 raised to k plus 1 minus 2 raised to k plus 1 is divisible by 5, when 7 raised to k minus 2k was divisible by 5. So we assumed that this was true, that is 7 raised to k minus 2 raised to k is divisible by 5, that is p of k, to prove that 7 raised to k plus 1 minus 2 raised to k plus 1 is also divisible by 5, right? So this was the proof principle of mathematical induction. Yeah, next is a small brief up. So there are the 4 strategies that we had: the direct proof, contraposition, contradiction, induction. The direct proof states that we assume P and we conclude Q. That is, let me just go back to the question that we did. Yeah, so we assumed this is P, this is Q. So we assumed that P was true and we had proven for Q. Next one was contraposition. So you assume that not Q is true and you conclude not P is true, which just says that because it's equivalent to the implication that P of P implies Q is equivalent to not Q implies not P. The contradiction was that if you had a statement, you assumed that the negation of the conclusion was true, and you proved that it wasn't true, so that the assumption was false, which just states that the original statement was true. The induction one was that you proved for P of 0, that's the base case, then you went till n, you assumed for P of n, and then you had proven for P of n plus 1, assuming the result from P of n. Remember the ladder example that we said, like if you know that you can climb the first step, and you know that from any step you can go to one higher step, we can prove for the whole thing, right? So that's that. A few questions I wanted you to try. Now you can pause here and try these questions. I'll just go over the discussion, like just a real quick discussion. What will these be? The first question is find the inverse, converse, and contrapositive for all the 4 statements that you have. The first question in itself can be solved by understanding what proposition P would be, what proposition Q would be, and the 3 different symbolic methods of depicting the contrapositive, converse, and inverse. And just look back to your notes again, how we wrote PQ, not P, not Q, and then write the converse, inverse, and contrapositive. I think whenever I'll be putting the slides up, or maybe next time we'll go over the question if anybody has any queries on that, or you can ask during the office hours or just email it to me. The second question is something interesting that you should look at, that all of them are proof methods. So the first one is that for all n that belong to integers, if n is odd, then prove that 3n plus 5 is even. Now you can take this as a direct question for direct proof. The second question is 3 does not divide 3n plus 2. So you're just essentially saying that 3n plus 2 cannot. So yeah, 3n plus 2 is not a multiple of 3. The third one is that if n mod 6 is equal to 3, then n mod 3 is not equal to 2. So what does this mean is, when you say n mod 6 is 3, you're essentially writing it down as, I'll just write it down here. So if I'm saying n mod x is equal to y, then I'm saying that n minus y is divisible by x. So it's essentially, this is the quotient, x is the quotient, and y is the remainder that you'll get when you divide n by x. Okay, so you're saying that when you divide n minus 3 by 6, so if n minus 3 is divisible by 6, then n minus 3 would not be divisible by 2. And the last one is, if there are 2 numbers, m and n, and that both are natural numbers, if m times n is greater than 100, then prove that n is always greater than 10 or m is greater than 10. It's an or that you need to look at. And understand the negation that you'll have when n greater than 10 or m greater than 10. When you negate both of them, so I'll just write it down. I'm writing the negation of that. So that will be n is so for the question D, make sure you know this because we'll be covering that in the next lectures. But for now, the negation of A or B is A dash, like negation of A and negation of B. Okay, so try the 8 questions, and if you have any queries, please feel free to email me. And I hope you stay safe and stay healthy. And yeah, just make sure you remember to, if at all you plan to email anything to me, make sure you have the ECS 20 right there so that I don't miss your emails, right? And I'm always eager to hear back from you, and please feel free to email me. Thank you so much and have a good week. And please finish the homework so that you can submit it on time, and stay safe. Thank you. Have a good one.